So we're going to be continuing learning about Gibbs free energy. And if you recall from the last time we introduced this, we have Gibbs free energy. You can go see Gibbs' grave at Yale if you're ever up there. It's a fun activity to do. But Gibbs free energy allows you to determine if a chemical reaction is spontaneous or not. It doesn't tell you anything about rate. It doesn't tell you anything about heat. It tells you if it's spontaneous. And the equation we looked at before the exam was our delta G is equal to delta H minus temperature times change in enthalpy. And remember, the temperature has to be in Kelvin. If your delta G was positive, this was considered endogonic or non-spontaneous. If your delta G was negative, this was considered to be exogonic or spontaneous. And if your delta G is 0, then you're at equilibrium. Similar to enthalpy, you can also calculate Gibbs free energy by doing the summation of Gibbs free energies of your products minus Gibbs free energy of your reactants. So we also had delta G can be equal to the summation of your Gibbs free energy of your products minus the Gibbs free energy of your reactants. And we made the little chart where you're looking at enthalpy and entropy and how, depending on if those are greater than or equal to 0, you can either have spontaneous at high temperatures, spontaneous at low temperatures, or non-spontaneous. Keeping in mind that temperature will always be in Kelvin. We did a few example problems and then we reviewed for the exam. So now I'm going to be presenting an additional equation that we can use for Gibbs free energy. So this is April, what's the date? 12th. So the new equations that we're presenting today are this Gibbs free energy standard. So we're at a standard temperature and pressure is equal to the negative of the gas constant times temperature times the natural log of our equilibrium quotient. So this is standard Gibbs free energy. Standard change in Gibbs free energy. This is a gas constant. This is often 8.314 joules per mole Kelvin. This is our temperature in Kelvin. And this is our natural log of equilibrium quotient. Of the equilibrium quotient. I'm thinking you've probably seen this in chemistry, even though it might have been a while. But if you were to rearrange this equation to isolate for just your equilibrium quotient, KEQ, then we would have e to the negative delta G standard over RT. And if you recall from the first day of lessons, KEQ is also this ratio of our products raised to their stoichiometric coefficients divided by the reactants raised to their stoichiometric coefficients at equilibrium. So these concentrations at equilibrium. Okay. So we have this where KEQ is equal to our products over our reactants. I switched C and D, it doesn't really matter. I just started writing the wrong one first. Is also equal to E to the negative delta G standard over RT. So if we have, let's look at KEQ. I'm making a table, KEQ, the natural log of KEQ, and how this impacts our delta G standard. Okay, so if we have a KEQ that is greater than 1, this ratio being greater than 1 is saying that we are favoring our products. So we can add another little line here that's like notes or something, but this is going to be product favored. Product favored, which makes sense because this is a ratio of our products raised to their stoichiometric coefficients divided by our reactants raised to their stoichiometric coefficients. So if you're greater than 1 in this ratio, you're favoring your products. Similarly, if you are equal to 1, then you are at this kind of perfect balance where you have your products and your reactants are equal. Products equals reactants. And if you are less than 1, then you are reactant favored. So if we have a KEQ that is greater than 1, it is a value greater than 1, then we have a positive natural log of KEQ. This is like a little bit of log chemistry. But if you have an ln of something that is greater than 1, it's positive. If you have an ln of something that is less than 1, it is negative. And if you take the ln of 1, it is 0. If we have a KEQ that is greater than 1, then our delta G standard must be negative. If we have a KEQ equal to 1, then our delta G standard must be 0. And if we have a KEQ that is less than 1, then our delta G must be positive. Which this is just some logarithmic math again. To get this value to be greater than 1, this would need to be a negative of a negative divided by RT to the E. Okay. So this is a nice table to kind of help you understand kind of where this is going and what it means. But one thing to keep in mind is this is all occurring at equilibrium. So we're only really looking at a snapshot in time of when we are at equilibrium. But equilibrium is not always what's happening. In fact, it's not often what's happening. A lot of times we are not at equilibrium, and we have another Gibbs free energy equation for when we're not at equilibrium. And it's similar to our Gibbs free energy equation when we are at equilibrium, but we have some additional considerations. So we have our delta G is equal to our delta G standard. plus RT ln of Q. So once again, this is still our change in Gibbs free energy at standard temperature and pressure. And change in Gibbs free energy at STP. This is our gas constant. This is our temperature in Kelvin. And this is the natural log of our reaction quotient. That should say natural, not naturat. Natural log of reaction quotient. So the reaction quotient mirrors your equilibrium quotient, your KEQ, except for it's not occurring at equilibrium. But your reaction quotient of Q is the same exact equation. Your products raised to their stoichiometric powers, their molar concentrations. Hold on one second. Okay. So our reaction quotient is representing the same exact equation, but it's not occurring at equilibrium. So these these concentrations are occurring at some point in the reaction that's not equilibrium. The way that we can compare Q and KEQ, and this question, I've seen this question come up on a lot of different exams, like MCAT. I've seen it on some FEs, depending on which type of FE you take. It'll come up in environmental chem. So we have this comparison where we're comparing our reaction quotient Q to our equilibrium concentration of KEQ. So when we compare Q and KEQ, it can tell us about the way the reaction will proceed, either forward or reverse. So there's several different ways that you can look at this. I'm going to present a couple just so it can help different types of learners. But when KEQ is greater than Q, then the reaction will proceed forward. And when KEQ is less than Q, the reaction will proceed in reverse. So I like to think of this as a line where the line's going to infinity. We're starting at 0. And this line is representing Q. So when we're on this line and we're somewhere along this line, and we have a value of KEQ, say this value is like 2, right? If we are lower than this KEQ, then we're going to try to go forward to meet this KEQ. So if we're at something like 1, 1.5, 0.4, we're going to proceed forward. We're going to try to meet up with this KEQ. We have over here, if the 0, the closer we are to 0, the more we're representing the fact that we have all reactants here. The closer we are to infinity, the more we're representing that we have all products. So essentially, if our KEQ is bigger, that means that if our KEQ is bigger than our Q, we need to proceed forward, produce some more of these reactants from the top to try to make our value bigger get us closer to that KEQ. So if we start at 0, we're all reactants. If KEQ is bigger, that means we need more products on the top of our ratio to get us a larger number to get closer to this KEQ. If KEQ is lower than us, that means that we are too product heavy. We are too high on the top of our ratio. We need to proceed in the reverse direction. And we need to try to increase the amount of reactants that we have, which is on the bottom of our ratio. So whenever I'm thinking about KEQ and comparing it to Q, I always think about this line. And if I'm lower than, I have to go forward to catch up. If I'm higher than, I have to go backwards to catch up. So I need to either increase my products or increase my reactants. Okay. So quickly, well, it doesn't have to be that quick. If we have KEQ is equal to 5, and we have Q is equal to 0.4, are we proceeding in forward or reverse? You can use the chat. Yeah. So we would be going forward. If we had KEQ is equal to 0.3 and Q is equal to 0.4, would we be going in forward or reverse? Yeah, reverse. If we had KEQ is equal to 0.4 and Q is equal to 0.4, would we be going in forward or reverse? Yeah, so we'd be at equilibrium. Thank you for participating, everybody. So if your Q is your KEQ, then that means you're at equilibrium. You might have a little bit of forward, a little bit of reverse, just because chemical reactions aren't like constant, but you would be not really proceeding in one direction or the other. Okay. When we're looking at our simple basic equation, so some molar amount of A plus some molar amount of B, going to forward and reverse of some molar amount of C plus some molar amount of D. And we have our reaction quotient where we have our products raised to their stoichiometric powers. What is the reaction quotient of this equation? Carbon dioxide gas plus water goes to carbon dioxide gas and hydrogen gas. So I want you to, I'm going to give you a few minutes. I want you to write the reaction quotient. Okay, great. Thanks, Kat and Emma. And you are right on the money. So first, you check if the equation is balanced. So carbons balanced, hydrogen's balanced, oxygens are balanced. If I had given you this equation written, I did this last year. If I give you the equation written like this, 2 carbon monoxide plus 2 waters plus 2 carbon dioxides plus 2 hydrogen, that doesn't actually change your reaction quotient at all, because if you just reduce it down, it should give you the exact same thing. Or if you're squaring everything, then you're not really changing your final answer. So it doesn't matter, as long as your equation is properly balanced, what stoichiometric coefficients are in front, because you should get the same answer since this is like a ratio. But it is important to make sure that it is correctly balanced.
I have a question.
Yeah.
We still put the 2's in the power exponent anyway, right? Just to show that if they were all 2's.
Yes, you could.
Because they're all the same.
Right. You could, because it shouldn't impact your answer, but in chemistry, you never want to have your numbers higher than they need to be. So like as a chemistry rule, if you have, if you had an equation that was like 8, 4, 2, and 2, you should never leave it like that, right? There's an obvious way to factor that lower. And I think that's just like a basic chemistry rule. And so if everything had a 2 in front of it, you should take the additional step, check that it's balanced, check that it's the lowest balance that it could be.
Okay. So we reduce it before we plug it into the quotient.
Right. I would always start by checking it's balanced and then checking if you can reduce it anymore. So yeah, just as like a chemistry thing to do. Okay, so yep, the reaction quotient is just these products over the reactants. So carbon dioxide to the first power, hydrogen gas to the first power, divided by carbon monoxide to the first power, and water to the first power. You don't need to write to the first power. I would take off points. That's not a big deal. And as I mentioned, it's really important to make sure that you're properly balanced. So checking that those really are ones at the beginning will be probably the most important step of the problem, honestly. Okay, so if I gave you concentrations, so your concentration of carbon monoxide is 1 molar, your concentration of water is 1 molar, your concentration of carbon dioxide is 2 molar, and your concentration of hydrogen is 2 molar. What does your Q equal? It's really easy math. Yeah, it's 4. This is also why it would be important to make sure that it's totally reduced, because if these were values of 2, you wouldn't actually get the same answer. So you would have 2 squared, which would be 4, times 2 squared, which would be 4, which is 16, over 1 squared, which is 1, times 1 squared, which is 1. So your answer would actually be 16, which it would be a square higher than it needs to be. So yeah, it's just important to make sure it's balanced and then reduce as much as you can, because your reaction quotient would be 4. If your KEQ is 0.6, will the reaction proceed forward? Which direction will the reaction proceed?
Backwards, reverse.
Yep. Yeah. Great. So thinking about my Q line, I'm going to go from 0 to infinity. And if my KEQ is here at 0.6 and my Q is here at 4, I'm going to have to go in reverse, proceed in the reverse direction. So this equation would proceed in the reverse as it's going towards equilibrium. So great, good job. Another way would just be KEQ is less than Q. This means it goes in the reverse. I don't like memorizing concepts, so that's why I'm always trying to figure out like, but what is it? Like, how do I know that without just memorizing it? So that's why I like the line, but you can also just memorize if KQ is less than. Great, great. That's an interesting thing about becoming like a teacher is like you start showing people the ways that you like learn to do it yourself, and like some people find it helpful, some people don't, because everybody's brain is different. So it's just interesting. Being a teacher is a weird thing to be. It's great. Okay, so let's work an example problem because I love those. If you are given nitrogen gas reacting with hydrogen gas to produce ammonia. This is a very common equation for working problems, but also in the real world. This is called the Haber reaction, and it's how we make ammonia. Sometimes it's really common. So if we're given this, and then we have concentrations of nitrogen gas of 0.04 molar, hydrogen gas of 0.09 molar, and ammonia is 0.5 molar. So remember, NH3 is ammonia, and NH4 plus is ammonium. Just always remember that. Okay, so if KEQ is 500, which direction is the reaction proceeding? So I'll let you work on that for a few minutes, and then we'll go over it. Okay, great. So it seems like some people are getting it. I will go over it. So first, we know that we're going to be working with our equilibrium quotient. I'm sorry, our reaction quotient here, because we don't know that we're at equilibrium. And so we know we have our reaction quotient here as our ammonia over our nitrogen gas and hydrogen gas. And we need to make sure that our equation is balanced before we go into our coefficients. So our equation is not balanced. We need to balance it by making, so we have 2 nitrogen here, we need 2 nitrogen here. Now we have 6 hydrogen, so we need to make sure this is 6 hydrogen, and then we can leave this nitrogen alone. So we know that our ammonia is going to be raised to the power of 2. Our nitrogen gas is going to be raised to the power of 1, and our hydrogen gas will be raised to the power of 3. Then we can plug in our concentrations. Ammonia has a concentration of 0.5 molar squared divided by nitrogen gas concentration, 0.04 molar to the first power. And then our hydrogen gas concentration of 0.09 molar to the third power. When you solve this, you get 8.6 times 10 to the 3. So a very large number. KEQ is less than Q, which means that we are going to be going in the reverse. Or if you look at the line, we have 0 to infinity of Q. Our KEQ is here at 500. Our Q is out here at 8 times 10 to the 3, 8.6 times 10 to the 3. So we need to go in reverse to get to this KEQ. So this KEQ is actually pretty high, and the reaction actually does favor products greatly over reactants. If we think about our KEQ being our, quotient of products to reactants, then when we have a KEQ as high as 500, then, sorry. Then we're greatly favoring our products. You can see too that here we're favoring our products. We have a much higher concentration of our products than our reactants, and it results in a very high Q value. All right. So let's look a little bit more at KQ. If we have a KEQ that is considered to be large, a large KEQ, this is greater than 1,000, where we're pretty much all product. We have such minimal comparative concentrations of our reactants that we're considered to be all product. Conversely, if we have a small KEQ, which is less than 0.001, then we're considered to be all reactants. Can you have a negative KEQ? No, you can't have a negative KEQ because it's a ratio and you're not really going to ever have a negative ratio. Your ratio can come very close to 0, but it's never going to go negative. You're never going to have a negative KEQ. If we have anything between this small KEQ of 0.001 and 1,000, we say that we have some products some reactants. Logically, the higher the value of KEQ, the more product favored at equilibrium. The higher the value of KEQ, the more product favored at equilibrium. One thing about working these problems, in addition, for you to incorporate Gibbs free energy in these problems, we always must have temperature and pressure information. Typically, temperature information, a lot of times we just assume atmospheric pressure, but we need temperature and pressure information because reactions will have different rates and they'll have different reactions at different temperatures and different pressures. Okay, so let's do another example. We have sulfur dioxide reacting with oxygen to make sulfate, I believe. Oops. And I want you to find KEQ given the following. We're at standard temperature and pressure. Concentration of sulfur dioxide is 0.9 molar. The concentration of oxygen is 0.35 molar. And the concentration of sulfate is 1.1 molar. Okay, so find KEQ. I'm gonna get a drink, be right back. Okay, sorry, I had to get a drink and give Beefy a little attention. So it seems like Emma got it. So great. For everybody else, I think maybe you didn't balance the equation. So first we need to balance the equation. We have 1 sulfur here, 1 sulfur here. We have 4 oxygen here, but we only have 3 oxygen here. So I'm going to put a 2 in front of here. Now I have 6 oxygen. I have 2. I can put a 2 in front of here because now I also need to balance the sulfur. So now I have 6 oxygen, 6 oxygen, 2 sulfur, 2 sulfur. I'm all set. Okay. That Kat, did you still get the same answer? Yeah, I'm trying to think of the rule for that. So I'm thinking that we might need to have it as whole numbers to do the coefficient, but I'm not sure.
I recall in my chem class, the professor always said not to balance it with fractions.
Not to balance it with fractions or
Yeah.
to balance it?
Mm.
Yeah, I think it might be a rule here. That you have to balance it with whole numbers, so your exponents are whole numbers. But I don't remember seeing that put together. I just always knew to do that. So let me check in the book. The book doesn't state that explicitly. Let me see what Google tells us. Let's see. Oops. So these are not using any fractions. It just says it to make sure it's balanced as well. Okay, it doesn't really seem like that is stating it outright either, but it seems that we need to make sure that we're balancing the equation using whole integers that are as reduced as possible without going to fractions. So I guess that's just like a general rule of thumb. I have always done that, but I didn't know that you had to do that. But now we're going to explicitly state that it needs to be as reduced as possible while still being whole integers. So, so therefore, I'm going to leave this as 2, 1, and 2. And then my KEQ becomes SO3 to the second power divided by SO2 to the second power times O2 to the first power. When I plug in my values for this, I would get 1.1 molar squared divided by, I don't know why I'm writing side, oh, this is sideways, divided by 0.9 molar squared times 0.35 molar to the first power. When you plug these in, 1.1 molar squared, then you get about 4.3, 4.27 as your KEQ at standard temperature and pressure. So this is our equilibrium value for our equilibrium quotient at standard temperature and pressure. If we were at a different temperature, it might be different. And if we were not at equilibrium, this would be our Q for our reaction quotient. One important rule, or here, I'll write these on the next page. So more about KEQ. For pure solids and pure liquids, these are not included in your equation, or they're included with a value of 1. So pure solids and pure liquids have a value of 1. And no matter what sort of power you put 1 to the 87th power, it's still going to be 1. So they're always going to have a value of 1. They're not really going to impact your equation. Because if you had, 1 times 32, it's still going to be 32. So I would encourage you to include them in your equation for your exam, just so I can see that you knew what you were doing. But you don't have to include them. It won't change your answer. Okay. So if we have, this equation, A plus some moles of B going to some moles of C plus some moles of D. If you reverse the equation, and your products become your reactants, then your K is inverted, which makes sense, right? Like kind of duh, but just if you reverse your equation at all, if you decide that actually your products are your reactants, your K gets inverted, it gets flipped. So another thing, when individual equations are combined, the equilibrium constants are multiplied to obtain the equilibrium constant for the overall reaction. The individual equilibrium constants, are multiplied, not added. They're multiplied to obtain the equilibrium constant for the overall reaction. To obtain the equilibrium constant. Oh, I'm sorry. This should say the equilibrium constant here. Multiplied to obtain the equilibrium constant for the overall equation. Okay. So I think That's good. Two. Okay. We're going to do one more example. So we have the Haber equation again, nitrogen gas plus hydrogen gas to create ammonia gas at standard temperature and pressure. Find KEQ given our delta G standard is negative 32.32 kilojoules per mole. And your R gas constant is 8.314 joules per mole Kelvin. So I'll give you like 5 minutes to work on that. And then you will go. Just a heads up, somebody's unmuted, whoever's whistling. It doesn't bother me, but just to let you know. So Layla, you're given temperature, and Kat, I don't know where your error is, but it should be a very, very high number, not a very, very low number. So make sure that you're doing, I think, your natural log math correctly. That might be where the issue is. If you turn your iPhone sideways, you get a lot more features on your iPhone calculator, just in case anybody's using their iPhone. It should be a really big number. So it's KEQ equals e to the negative delta G standard over RT. No. Yeah, Elizabeth, you're very close. I think Emma and Jordan got the same answer, but you're slightly off. I will start going over it instead of harboring more confusion. So for this problem, we know that our delta G standard is equal to RT ln of KEQ, or KEQ is equal to e to the negative delta G standard over RT. So we want to find KEQ, so we're going to use this equation. We have e to the negative 3.32 kilojoules per mole divided by 8.314 joules per mole Kelvin times 25 degrees Celsius plus 273 degrees Kelvin. So I'm converting standard temperature and pressure into Kelvin. If you know standard temperature and pressure is 298 Kelvin, you don't have to do this math. That's not a big deal for me. But one thing that's coming up is I have kilojoules here and joules here. So I'm going to need to convert one of those. I'm just going to pick one. So I know that 1 kilojoule is 1,000 joules. So therefore, I have e to the positive, let's see, 33,000, right? 33,320 kilojoules or joules per mole divided by 8.314, or yeah, 8.314 joules per mole Kelvin times 298 Kelvin. Yeah, so standard temperature and pressure is on your memorized sheet. You should know what standard temperature and pressure are. No, STP is 25 degrees Celsius, which is 298 Kelvin. I'm pretty sure. Yeah, so it's 1 ATM. Oh, oh God, that's confusing. Hold on. Okay. So when you Google it, it's saying STP is defined as 273.15 and 100 kilopascal or 1 ATM. But standard state conditions, standard ambient temperature is 25 degrees Celsius. So it seems like there's like a disconnect in what I'm saying. So standard ambient temperature and pressure is 25 degrees and 1 ATM. Standard STP based on the 1982 definition is 0 degrees. So I can see where this confusion is coming from. So, okay, I'll say here that this is occurring at ambient temperature and pressure to avoid any like any confusion about that. But I guess so STP is defined as 0 degrees Celsius and ambient is 25 degrees Celsius, or like steady state temperature. So 0 degrees Celsius is freezing. 25 degrees is like room temperature. So there seem to be kind of two different ways of talking about STP. So a standard condition is 25 degrees. Standard state would be 0. So I'll say, so we'll stick with the memorized sheet and the definition. So STP will be 0 degrees Celsius and 1 ATM. And standard, so in ambient temperature and pressure will be 25 degrees Celsius. Okay, so yeah, that might be why some people are getting different answers here. But we're gonna, for this problem, we're gonna stick with 25 degrees Celsius. And if you work this out, you get about 6.6 times 10 to the 5 as your KEQ value. So is this value considered to be a high KEQ or a medium KEQ or a low KEQ? Yeah, so this is a high KEQ. This is very high. And this is going to be considered all products. So at ambient temperature, at room temperature, the Haber process greatly favors our products. If you notice here, I didn't have to balance the equation and it had no consequence on my final answer, but you do need to balance the equation always. Even though if you work it this way, your delta G is based on an already balanced equation. So it won't really have an impact. Did you do it to the power of E? I'm not sure. Did anybody else have that same issue that they fixed? I'm not sure.
Oh, I got one when I didn't convert the 33.32 to joules.
Okay.
That's the only thing. So if you put 33.32 instead of 33,320.
Yeah. Okay. Yeah. So you make sure to convert joules and kilojoules, things that might, yeah. It helps because some people work it the same way and get the same wrong answer. So it's nice to hear. Thank you for your help. Okay. So this is a high KEQ. It's going to favor constants at ambient temperature at equilibrium. But one thing to keep in mind that Thermodynamics, the Gibbs free energy and enthalpy. Thermo tells about direction. It tells us which way it's going to go and if it's endothermic and exothermic, but it doesn't tell us the, and it can tell us the extent of the reaction, but it doesn't tell us anything about rate, not rate. So even though this KEQ is high, and even if this is an exothermic reaction, it still might take 40 years to proceed. Just because it's spontaneous doesn't mean that it's quick. So remember, we have no information about rate. This is where we have to get into our rate of reactions, our catalysts, more things that you'll see in environmental chem. But Gibbs free energy and enthalpy only tell you about endothermic, endogonic. They don't tell you about the rate of the reaction. Okay, so on Wednesday, I'm going to do a little more example problems, a little more complicated. And then, so here's an announcement. I should have made this at the beginning. I will not be able to have class on Friday. So there's no class on Friday. I have to give a presentation to a former group I was a part of in grad school at Duke. So I'm not going to be able to present class on Friday. No class on Friday. So no class on Friday. I'll send this in an email reminder with the poll for our final exam, but you do not need to go to Thermo on Friday. I would encourage you to spend that time studying for Thermo, studying for your other exams. I know it's a busy time in the semester, so I'm sure everybody can enjoy a day off, but there is no class on Friday. Alert, 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 no class on Friday. Yeah, you can see the screen again, sorry. And so on Wednesday, we'll do more problems. And yeah, thank you. Then we will continue next week. So you have nothing to do for Thermo on Friday, except for maybe just make sure you're keeping ahead with the material. So yeah, nothing for Thermo on Friday. Any questions about that? Okay, so this, if you want the next step, this is e to the positive 13.4 roughly is what you should get for this equation, which then gives you about 6.6, 6.9 times 10 to the 5. Okay, any questions before we adjourn? Okay, then have a great rest of your Monday. I will see you on Wednesday morning. Remember, standard temperature and pressure is actually 0 Celsius and ambient temperature is 25 degrees, like room temperature. So sorry for that confusion, and I will see you all on Wednesday. Have a good day.
Have a good day. Thank you.
Bye, thanks. Yeah, I always feel like it should be 25 degrees. Like, how is standard freezing? Whatever.